All right, so let's start doing like Delta-Wye transformation. But before doing like Delta-Wye transformation, let's have like a quick review of like what Delta-Wye transformation was, right? Basically, we said if we have a circuit that looks like a delta, let's call it A, B, and C, and this is R1, let's just say this is R2, and this is R3. We can always replace this circuit by a circuit that looks like an upside down Y. And let's just call this RA, RB, and RC. And we said if we go from delta to Y, we always create one node that's in the middle, right? So if we have a delta circuit, we have 3 nodes. But as soon as we go from delta to Y, we have 4 nodes. And we said, given one of them, we can always find the other one. And we had like some simplified like formulas for it. So let's just say R1, R2, and R3 are given. Basically means that delta is given, and we want to go to Y. That's the simple one. To find RA, we're going to look at RA, and we're going to see it's between R1 and R2. So the numerator would be R1 times R2 divided by R1 plus R2 plus R3. RB is between R1 and R3. So the numerator here is just going to be these two adjacent resistors. So it's going to be R1, R3 divided by R1 plus R2 plus R3. And RC, again, it's between R2 and R3. So it's going to be R2, R3 divided by R1 plus R2 plus R3. Right? Again, I highly recommend you guys actually put down these things on your cheat sheet. Like I said, I'm very bad at like memorizing things, but that's the way to remember it. If you don't remember it, if you don't have it on your cheat sheet, you can always go back to the equations that we had and try to like solve those equations. You're going to get the same result. We also talk about like very special case where R1 was the same as R2 was the same as R3. Let's just say all of them are like 6, for example. And we call that R delta, right? And then we said, if all of them are the same, the values for the resistor in Y circuit must also be the same. So we have RA the same as RB, the same as RC, and we call that RY. And we could compute RY using like one of these formulas. For example, let's just use this one. If I wanted to compute RA, I know I have R delta times R delta divided by R delta plus R delta plus R delta. So I have R delta squared divided by 3 R delta. R delta and R delta cancel, so I have basically R delta divided by 3. So that's 1/3 R delta, right? And that was a special case, right? We said if we have RA, RB, and RC, which means we're given the Y circuit, we can always go back to the delta, right? And the way that we can do it is that R1, R2, and R3. The numerator for all of them is just all possible 2 combinations of like these resistors, right? So the numerator over here is RA, RB plus RA, RC plus RB, RC. And it's the same for all of them, RA, RB, RA, RC plus RB, RC. Same thing for R3. To find denominator, if I want to find R1, I got to see like where R1 is looking at. It's looking at this RC over here. So I'm going to put this RC down here. For R2, R2 is looking at this RB. So it's going to go right here. And R3 is looking at this RA, so it's going to go down here. Right? And the special case, again, is when RA is the same as RB is the same as RC, which we know it's RY. So if I plug it in here, I can see that R1 must be the same as R2, must be the same as R3. And that's basically R delta. Right? So if I plug it in here, I have RY squared plus RY squared plus RY squared divided by RY. So I have 3 times RY squared divided by RY. So it's 3 times RY, which we already knew it from here. Right? So these are the things that we talked about before. And we said all these equations came from that very basic equation of like equivalence of like these two circuits. Right? These were the solutions for it. Okay? We did one example like last time. Let's do a few more examples to just make sure we're all on the same page. Is this clear what's happening over here? Yes? All right, let's do one more example. Let's just say I'm given this circuit. I have two 12 ohms resistance. Up here, another 12 ohms and 12 ohms over here. It's followed by a current source with value of 4 amps. And then we have a 12 ohms resistance over here, 12 ohms resistance over here, 12 ohms resistance here, a 12 ohms here, a 12 ohms over here. And the question is asking me, what is power supplied by a current source? Okay. Is the question clear? We're given a circuit. We're asked to find power supplied by the source here. Let's look at the circuit for a second. What are our observations? What are the things that we immediately see in the circuit? What is it? The very first thing that we observe is that if I look at the top square, that is actually a delta. Why? Because let's just call this A, right? This is exactly A, right? Because they're actually connected with a wire. There is no potential difference. So these two are no different nodes. They're exactly the same node. So if I call like this thing A, if I call this thing B, call this thing C, I can basically grab these two things and glue them over here, and nothing will happen, right? Because there is no potential difference there. And this thing over here is indeed a delta circuit, right? How about the one down there? Is that a delta as well? That is a delta, right? With this exact same logic, I can basically glue the bottom node and make it look like a delta. So that is exactly a delta. But for the sake of like this problem, let's just only look at the one on the top. Okay? We can either do the top or the bottom, right? So let's just stick to the top. What else do we see in this circuit? What else do we see? Is there anything else to see? Yes. How? They're not in series. Why? Because if these two were in series, whatever current that's passing through here should pass through here. But I have like this line over here, so I have a leakage of current through this here. So the current through here is not going through here. So they're not in series. With the same logic, these two are not in series either. Somebody over here wanted to say something. No? How about these two? What are they? They're in parallel. Why? Let's go back and review the definition of parallel. Parallel means they're sharing the exact same head and exact same tail. Well, if I look at the head over here, that's exactly the same as the head over here because it's connected by a wire and the potential difference for a wire is 0. Look at the tail down here. It's exactly the same as this guy. Right? So they're sharing the exact same head and tail. Right? So they're in parallel. How about these two? The same thing, right? It's exactly the same thing. So if I have these two, I have 12 in parallel with 12. Down here, I have another 12 in parallel with 12. We can just plug it into the formula as 12 times 12 divided by 12 plus 12. Or since they're actually exact same value, the equivalent would be half of it, right? So it's a 6. So this is 6 ohms, and this is 6. For a second, let's just think about the locations of like these two 6 ohms and how they're actually connected to each other. Remember, this 6 ohms, the one on the top, is going to go from here between this node and this node. And this 6 ohm will go from this node to this node down here. So what is the relationship between these two? They're in series. So I can combine them and get 6 plus 6, which is a 12 ohm resistance. Right? This looks pretty busy. Let me just redraw the circuit really quickly. So what I have here is a 12 ohm resistance. I have this 4 amps. If I have a Y equivalent should go between A, B, and C. Right? So it should go right here. Right? So let's just call this A, this B, and this C. So it's going to go right between these nodes. Right? This is B. This B is connected to this 12. This C is connected to this 12. And the rest, we're good. Right? The only thing we have left is just the values of like these resistors. Right? I got to like know what those are. But we already know. Why? Because if you look at the delta circuit, the delta circuit has resistors are all equal. So if I go from delta to Y, what is the value of the Y? It's 1/3 of it, right? If I don't remember that, I can always go back to the formula, right? Look at the adjacent ones, multiply them out, divide them by whole thing. For example, in this case, if I want to find the top one here, the adjacent ones are these two 12s, right? So it's 12 times 12 divided by 12 plus 12 plus 12, which is 144 divided by 36, which is again a 4, right? So if our delta is 12, then we know our Y is 1/3 of our delta, which is 12 divided by 3, and it's a 4. So I know these numbers. These are 4. Right? So far, are you guys with me? Yes? Everybody with me? Yes. Sure. So the original circuit here is the black one, right? What I'm trying to do is that I'm trying to remove the delta and replace it by its equivalent, which is a Y circuit, right? Do you agree this point A here is the same as this point A is the same as this point A? Because they're wire, right? I call this point B. I call this point C, right? I know my Y is going to go between A, B, and C. So that's exactly like how it went. This is A, this is B, this is C, right? All I need to do is to find like the values for these resistors. I could either use like the general formula that I had or the special case, because the values of the resistors for the delta, they're all the same, and they're 12, right? So I know that's basically like 1/3 of it, which is 4. And that's how I get this circuit. Is that clear? Okay. Look at this circuit. This is much simpler. What do we have here? Do you agree I have like this 12 and this 4 in series? With the same logic, this 2 and this 4, they're in series. Let's just write it down. I have these two in series. I have these two in series. What else do we observe? Can we say this 16 that I have over here is in parallel with this 16 that I have over here? Can I say that? Can I? Yeah, they're sharing the exact same head and tail. So I can replace them by like the equivalent here. This is 16 in parallel with 16, which is an 8, right? Again, they're exactly the same, so the equivalent would be half of it, right? Let's redraw the circuit. I have a 12 ohm. I have 4 amps. I have a 4. I have an 8, which I know this 8 is this 16 and 16 in parallel, right? What is this circuit? This is a very familiar circuit. It's a current divider, right? Remember what current divider was? Current divider was a current source followed by 2 resistors in parallel. That's exactly like what it is. As soon as I combine these two, I have the very familiar current divider for. So if I combine them, I have 8 plus 4, which is a 12. And I can simply find current through here. What is current through here? Well, current through this branch is proportional to the value of the resistance here, 12, divided by 12 plus 12 times 4, which is 2 ohms. There was a very simple way of like obtaining this 2. How? Look, this 4 amp is going to go all the way through here. It's going to get to this point. And if you look at like the resistors over here, they both are like 12. So the current is going to split. But since these two values are exactly the same, it's going to split equally. So without even using this current divider, I know the current through here should be like 2, and current through here should be 2. Right? Just a simple KCL. Right? But also current divider tells that to us. This is a current divider. Right? Now I know current through this 8 ohms resistance. What is voltage across it? What is voltage across it? Let's just call this V. What is V? We have Ohm's law, right? So V equals Ri, which is 8 times 2, which is 16 volts. Okay. I really don't need this, but I'm doing it because I want to just show you guys something. I want to review something with you guys. If this V across this 8 is 16, what is voltage across this? 16, right? What is voltage across this guy? Still 16. Why? Because they're in parallel. If I have two things in parallel, voltage across all of them are the same, and that's the same as the voltage across the equivalent. Okay? But essentially what I'm looking for is voltage across this current source, right? Because I'm looking for power supplied by this guy. I know current through it, so essentially the question is, what is voltage across this current source? What is it though? Let me find voltage across this guy, and let's call it V total. What is V total? What is V total? Again, it's the value of the resistance. In this case, it's 8 plus 4 times current through it, right? Which is 24 volts. So if I assume this polarity over here, and let's just call it VI. What is VI? What's the value of VI? VI must be 24, right? Because these two are in parallel, so whatever voltage I have here should jump across this. But there's like another way of seeing it. We can write a KVL over here, right? So if I write a KVL, I have minus VI plus V total should be 0. Therefore, VI is V total, which is 24. Right? Remember, if we have any element, this is my element, I have this current. If the current hits the negative sign, what is the value of power? The value of power is negative, or what it means is that the power is being supplied. So this means like power is being supplied. But remember, the question is asking me, what is power supplied by this thing? So I already know this power should be negative, right? Well, let's just see if we can actually get it negative. I have P equals VI. I already know I. What is I here? 4. But what is V? What is V? It's negative 24, because we're seeing the negative sign first. So it is negative 24 times 4, which is minus 96 watts, or 96 supplied. Right? Right? Yes. The direction that current's going, it's given to me. It's going upward. The direction of the current source, it's going upward. It splits and it's going down. Right? Right? Again, if I don't know, I can assume the direction of this I over here is upward. I can assume that. When I'm obtaining this I, instead of getting 2, I'm gonna get negative 2. Right? but this is the direction that gives us like positive value. That's why we get like 2. Any question? Any question? Yes. Sure. Over here. So we have 2 different ways of looking at it, right? The first way is I have 4 amps going into this node right here. And since the value of the resistance over here is the exact same as value of the resistance here, current over here must be equal. And it should be half of this. That's one way of doing it. Another way is that, look at the circuit. The circuit is a current divider circuit. So I can use the formula for current divider. What is the formula for current divider? The formula for current divider is that current through this branch is proportional to the value of the resistance on the other branch divided by the whole thing times the value of the source. It's 12 times 12 plus 12 times 4. That's a current divider formula, right? Any question? Any question? Yes. That's KVL. That is a KVL. Right? Any question? Any question? Is that clear how it works? So if I give you guys this on the exam, you're able to do it, right? Yes? No? So does that make sense to everybody? Should I move on? Let's do one more example. Let's just say I have this source over here, which is a 4 milliamps, and it's followed by this circuit. Say 12K, 12K. I have another 12K, a 12K down here, 12K down here, and this guy. What I'm after is the out here. Let's look at this circuit a little bit. What do we observe? The first thing we see is that there is a delta on the top, right? The second thing we observe is that there's a delta on the bottom, right? Which one should I choose? The one on the top or in the bottom? Which one do you think I should use Delta-Wye transformation for? Top. Why? Because as soon as I use the Y transformation for the bottom, I'm going to lose that V out. There is a way to go back and get it, but Y would be basically make our life like much harder. So let's go and write the Y transformation for the top circuit. Again, remember this is A, which is the same as this A, which is the same as this A. This is B, and this is C, right? I'm going to have that circuit replaced by this guy. Let's call this RA, RB, and RC. And let's call this guy R1, R2, and R3. There's a reason I'm doing this, because I want to go back and use the actual formula and not the shortcut that we learned. Right? I want to use the actual formula. If I want to find RA, what are the adjacent ones? What are the adjacent ones? Again, I'm going to look at node A and see what's connected to node A. What are the things that are connected to node A? R1 and R2. Right? Remember, I can basically grab this thing and glue them both over here. So that would be R1, R2 divided by R1 plus R2 plus R3. Right? Which is 12 times 12 divided by 12 plus 12 plus 12, which is 4K. We already knew it, right? Because that's a delta with equal values, so y should be 1/3 of it, right? We already knew that. But the actual formula also tells us the same thing. How about RB? If I want to find RB, what is the formula for it? Given this configuration. I want to find this guy. What is it? It's R1 and R2. So R1, R2 divided by R1 plus, sorry, that's R1 and let's just call, actually this is R3, right? So this is between R1 and R3, right? So this is R1, R2 plus R1, R2, and R3, right? RA is between R1 and R3, so I have R1, R3. RB is between R1 and R2, so I have R1, R2. Again, it's 12 times 12 divided by 12 plus 12 plus 12, which is 4K. It's 144 divided by 36, which is 4. How about RC? If you look at RC, RC is in the middle of R2 and R3, right? So that would be R2, R3 divided by R1 plus R2 plus R3. 12 times 12 divided by 12 plus 12 plus 12, which is a 4K, right? So you can either use the actual formula, which is this guy, or you can use like the shortcut that we learned. Is that clear how I computed this? Right? I'm going to look at like whatever I want to find and see like where that is located in between. Right? It's located, for example, between this one, and that gives me this RA. So let me redraw the circuit. Let me redraw the circuit. I have this 4 milliamps. Again, I have this A. I have RA, which is 4K. I have RB, which is 4K. And I have RC, which is 4K. This B is connected to this 12K. The C is connected to this 12K. And then I got nothing else. Okay? Let's solve this circuit in a very easy way. And then we're going to go through the steps and make sure that we all understand all the steps. Look what's happening over here. I have this 4 milliamps current source that's flowing through here. It's going to get to this point A, and it's going to flow through this 4K. So what is the current at this node right here? It's this 4 milliamps, right? This 4 milliamps got a split between these two branches. But look, these two are in series. I can combine them. That's a 16. These two are also in series. I can combine them. So this is 16 and this is 16. So what happens to this 4 milliamps current? It's going to split in half. So it's going to be 2 milliamps down here and 2 milliamps down here. As soon as I know the current through here, I know current through this is the same as current through this because they're in series. So what is voltage across this? That's 2 times 12. That's 24 volts. Right? So that's how it works intuitively. Right? Does that make sense how it works intuitively before I write down all the steps? Is that clear? So let's just go through like all the steps and see how we can actually compute all the steps. So if I wanted to do every single step, well, the first step is these two are in series. So I have 12 plus 4, which is 16K. These two are also in series. So I have 12 plus 4, which is 16K. What else do I have over here? I have this 16 and this 16 in parallel. I can combine them. So I have 16 in parallel with 16, which is going to be an 8. Right? And again, what I'm after is voltage across this. But since I combine this thing, I have only from here to here. And let's call that V prime. Basically from this point to this point. That's called V prime. Okay? Which is across this 8. So let me redraw the circuit. So what I have here is 4 milliamps. I have this 4K. And I have this 8K resistance. And voltage across this is V prime. Right? What is current through here? What is current through it? It's 4 milliamps, right? Because I have like this current going through this guy. Therefore, what is V prime? It's 8K times 4 milliamps, which is 32 volts. Right? But 32 volts is voltage across this 8. Therefore, it is voltage across these two or these two. Right? Because they're in parallel. So whatever voltage I have for this equivalent should be across these two and these two. Right? If I have voltage across these two, 32, what is voltage across this 12K? What kind of circuit do I have? Somebody said it. What is it? It's a voltage divider. Right? I know voltage across both of them. I know voltage across both of them is 32. So I know voltage across this guy. Right? There's another way of doing it. I know voltage across both of them is 32. Therefore, current through this thing is 32 divided by 4 plus 12. Right? Which is 2. What is the voltage across this guy? It's 12 times 2. Right? So let's just do let's just do both ways. First way is voltage divider, which means voltage across both these is 32. Therefore, voltage across the 12K is 12K divided by 12K plus 4K times 32, which is 24 volts. Second way is to use Ohm's law. I know current through this guy. Let's just call it I double prime. I know I double prime is V prime divided by 4K plus 12K, which is Ohm's law, which is 32 divided by 16, which is 2 milliamps. Therefore, again, use Ohm's law again, voltage across 12K, it is 12K times 2 milliamps, which is 24 volts. Right? Right? Any question? What I would like to point out here is that if I look at this circuit is Ohm's law, right? Whatever current I have through here is just going to flow through that 4K and then flow through that 8K, so I know voltage across each one of them if I want to. Right? But what if my circuit looked a little different? What if my circuit looked like this? I had this 4 milliamps. Then let's just say I have like another 4K here, and then this 4, 4, 12, 4, and 12. Basically, I have exact same circuit. I only have like this one extra. What's going to happen? Do I still have this Ohm's law? Well, obviously not, right? Basically, I have these two I can combine. I have these two I can combine, right? So my circuit would look like this. This is going to be 8, right? What is the circuit? We're familiar with this circuit. That's a current divider. We can no longer say if I have like all 4 milliamps, it's going to flow through here and it's going to split equally here. Because as soon as I have like this 4 milliamps, it's going to get to this node. Some of it is going to go through here, and some of it is going to go through here. Let's just call current that's going through here, I don't know, I, which is this guy, right? Right? What is this I? Well, I is a voltage divider. It's a current divider, so it's 4K divided by 4K plus 8K plus 4K times 4 milliamps, right? That's 16 divided by 16, so it's 1 milliamps. Right? Now I know this I here up to this point is 1 milliamps. But if I look at these two, again, these are exactly the same. So current here, if I call it like I double prime would be half of it. Because this 1 milliamp this time is going to split between these two things equally. So adding one resistance in between can change the entire problem. This 4 milliamps is no longer going to flow through here and then split. Portion of it is going to go through here, and then that's going to split. Right? And obviously, since the resistance over here is higher than the resistance over here, current through here must be less than the current through here. Keep that in mind. Current always takes the path with the least resistance. So most current is going to flow through here because the resistance is actually much less than the resistance over here. Right? Is that clear what we're doing? Yes? No? We good? So that is basically Delta-Wye transformation. We just need to like spot a delta, and as we need, we can actually like replace it by the y. Yes. Current divider formula holds. You can always like apply the current divider formula. Oh yeah, you can still do that. Yes, yes. You just need to like go back and apply like the original formula, just like what I did over here. Right? So what we're going to be doing next lecture, we're going to start talking about like node analysis, which is a systematic way of solving any circuit that we have. Right? So we're going to talk about like node analysis, then we're going to move on to like mesh analysis, which is another systematic way of like solving any circuit. It just exploits different methods. Node analysis uses KCL. And even though KCL is solving for I's, if you use like node analysis and write all the KCLs, what you end up getting, you're going to get node voltages. And when we're writing like KVLs for the mesh analysis, even though we're writing KVLs, we're going to end up getting like loop currents. So what we're going to be doing is that we're going to go through like all these steps. We're going to have like a recipe for like node analysis. We're going to have a recipe for like mesh analysis. And then we can apply like these two methods to whatever problem that we have. We're going to compare these two methods, and we're going to learn like when we can use one over the other one. And that's basically what we're going to be doing like next week. I'll see you guys next week.